Good morning, students. Today, our topic is Raoult's law as a special case of Henry's law. We know that Raoult's law P is directly proportional to X, means the quantitative relationship between the partial pressure and mole fraction. So, this relationship is known as Raoult's law. Partial pressure is directly proportional to mole fraction. So the Raoult's law tells us about liquid in liquid. Both are means the solvent and solute. Both are in liquid state. Liquid in liquid. So what is that Raoult's law statement? For a solution of volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction present in the solution. So this is the Raoult's law. And here let me take one proportionality constant. So this is the partial pressure. So let me take Pi is equal to and Xi, and let me take a proportionality constant P naught I. So Pi is equal to Xi into P naught I. So this is the Raoult's law. So what is that Henry's law? The Henry's law, the partial pressure of gas in vapor phase is directly proportional to its mole fraction. So here also P is directly proportional to X. So the Henry's law statement is at a constant temperature, the partial pressure of the gas in a vapor phase is directly proportional to mole fraction in the solution. So let me take here one proportionality constant. P is equal to partial pressure and proportionality constant KH and X. So this is the Henry's law. So if you compare both Raoult's law and Henry's law, the partial pressure of the volatile component is directly proportional to its mole fraction in the solution. So here only the KH differs from the P naught I. So if you take P naught I, so it belongs to Raoult's law. Instead of P naught I, if you take KH, it belongs to Henry's law. Only the KH differs from P naught I. Thus, the Raoult's law becomes Henry's law when KH become P naught I. Next one, vapor pressure of solids in liquids. So what is that vapor pressure? First of all, we have to know that vapor pressure. Vapor pressure means, for example, if I take one container, sealed container. So in that sealed container, I am taking pure solvent. And it is a volatile solvent, means it can easily evaporate. The liquid can convert into gas. So here at a given temperature and under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid is called vapor pressure. So this liquid convert into gas, means convert into vapor. So that vapor exerted the pressure over that liquid is called vapor pressure. So here pressure exerted because of that vapor molecules is called vapor pressure. Let us come to here. So here I am taking pure solvent, means I am taking only one component solvent. So it is a volatile solvent. So here in this I am taking the 1 mole solvent and 1 mole solute. 1 mole solvent is a volatile solvent and 1 mole solute, it is a non-volatile solute. So here I am taking half of the solvent and half of the solute. So in pure liquid, the entire surface, so this is the liquid surface, the entire surface is occupied by the molecules of the liquid. For example, if I take it as a water, so that entire surface is occupied by water molecules, means there is no other component, there is only one component, that is solvent. Means here I am taking for example water, so this surface is occupied by only water molecules. So this is the water, and if I add one non-volatile solute, the non-volatile solute is NaCl. For example, I am taking NaCl. NaCl is a non-volatile, and H2O is a volatile because it can evaporate, but NaCl cannot evaporate. So if I add non-volatile solute, means NaCl is added to a solvent, then the vapor pressure of the solution is only from the solvent. Because here what happening, after adding the NaCl, so see here these are the NaCl molecules, the red marks, NaCl molecules. In above picture I am taking a different color for solvent and solute. So here for that solute I am taking red color, and for solvent molecules I am taking blue color, but in above picture I am taking a different colors. So after adding the NaCl, means after adding the solute, the vapor pressure of the solution at a given temperature is lower than the vapor pressure of the pure solvent at the same temperature. So here after adding solute means NaCl, that surface of solution is occupied by both molecules, solvent molecules and solute molecules. So here at the surface of solution, number of solvent molecules will be reduced. Consequently, the vapor pressure also reduced. See here, if you compare both, this is the pure solvent and this is the solution. So in that pure solvent, that surface of solvent occupied by only the solvent molecules. So more number of molecules are converted into gas. Here the number of gas molecules are more, so then the exerted pressure also be more. So after adding the solute, the surface of solution occupied by both molecules, solvent molecules and solute molecules, only the solvent molecules are converted into gas. Means the solvent is a volatile, solute is a non-volatile, only the solvent is a volatile, only that solvent molecules are converted into gas. So here at that surface the number of solvent molecules decreases, means less number of solvent molecules are converted into gas, so the number of gas molecules are decreased. So here the exerted pressure also be decreased, because the gas molecules are less here, but here the gas molecules are more, and here the gas molecules are less. So after adding the non-volatile solute to the solvent, the exerted pressure will be decreases. So here the decrease in vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution. irrespective of its nature. So the vapor pressure is depending upon the quantity of non-volatile solute. So which non-volatile you are taken is doesn't matter, but how much of non-volatile solute you taken is considered. For example, a decrease in vapor pressure of water by adding 1 mole of sucrose to 1 kg water. So here water is a volatile solvent and sucrose is a non-volatile solute. And we know that Raoult's law, for any solution the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. P is directly proportional to X. So here I am taking a binary solution, means the solution contains two components. So here one component is solvent, so that solvent is represented by 1, and another component is solute, so that solute is represented by 2. When the solute is non-volatile, so this solute is a non-volatile and solvent is a volatile. So when the solute is non-volatile, only the solvent molecules are present in vapor phase, because only the solvent molecules are converted into gas. So in that gas phase we can find out only the solvent molecules. So for that, here I am taking, this is the vapor pressure on y-axis, on x-axis I am taking the mole fraction of the solvent. So here it is a 0 and here 1. If I take a middle point, so there is a half mole fraction of solute and half mole fraction of solvent. So if I go from left to right, the mole fraction of solvent increased, so then it reaches 1, and we know that sum of mole fractions is equal to unity. So here we got 1, means here we have only the solvent mole fraction, only the solvent mole fraction. The mole fraction is 1, so at that mole fraction 1 we have only the solvent. So here the vapor pressure, so this is the vapor pressure, so that vapor pressure is pure solvent vapor pressure, means here there is no solute, there is only solvent. If the mole fraction of solvent increases, then the vapor pressure also increases. So here P1 is a vapor pressure, and X1 is a mole fraction, and P1 naught is a vapor pressure in pure state, So according to Raoult's law we can write that P1, according to that Raoult's law we can write that P1 is directly proportional to X1. If you take a proportionality constant here, P1 is equal to proportional X1, P1 is equal to X1, and the proportionality constant P1 naught. So this is the Raoult's law. And next one, liquid solutions. So on the basis of Raoult's law, the liquid solutions are two types. Number 1, ideal solutions, and number 2, non-ideal solutions. ideal solutions and non-ideal solutions. Let us take first one, ideal solutions. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. The ideal solutions properties are, when the two components, I am taking component A and component B, component A and component B are mixed to form solution. So these two are mixed to form solutions. These two, A component and B component, these two components are mixed to form solution. And the change in enthalpy will be 0. The change in enthalpy will be 0. So the change in enthalpy, delta mix H. Delta H is change in enthalpy. So delta mix H is equal to 0. The change in enthalpy 0. It means no heat is observed. No heat is observed or released. So there is no heat observed, no heat released when the two components are mixed. And come to the volume. The volume of solution will be equal to the sum of volumes of two pure components. So here delta mix volume V is equal to 0. So the delta mix V also be 0. So here I am taking component A and component B now. So here this is the component A and this one is component B. So component A, let me assume it as a solvent, and component B, let me take it as a solute. So here the volume of solution will be equal to the sum of volumes of two pure components. So delta mix V is equal to 0. So two components means A component and B component. So in pure A component, so this is the pure A component, there is no B component. So in pure component A, intermolecular attractive interactions are A and A, means there is a intermolecular attractive interaction between the A and A, means between the solvent and solvent, and in pure component B, so this is also pure component B. Why it is called pure? Because it is a only one component, so that's why it is called pure. So in pure component B, the intermolecular attractive interactions are BB, means the attractive interactions between the solute and solute, In pure component A, the intermolecular attractive interactions are solvent and solvent, and A and A. And in pure B component, the intermolecular attractive interactions are B and B, means solute and solute. Then if we mix both to get a solution, so I'm going to mix both component A and component B, so I'm getting the solution. So this is the solution. So in that solution we have A component and B component. So in that resulting solution there are three types of interactions, three types of interactions. So the three types of interactions are A and A, means between the solvent and solvent, and another one, because in this solution we have A component and B component, means solvent and solute. So there are three types of interactions. One type is A and A, means interaction between intermolecular interactions between A and A, means solvent and solvent. And second type B and B, means between solute and solute particles, solute and solute particles. And third type is AB, means between solvent and solute, between solvent and solute, because in this solution we have solvent and solute. So there are three types of interactions. A and A means solvent solvent, BB means solute solute, AB means solvent solute. So here, if these three means AA, BB, AB, if these three intermolecular attractive interactions are same, it leads to formation of ideal solutions. Ideal solutions. Yeah, because AB have same size, shape and character. So that A and B, the both components having same size, shape and character. But a pure perfectly ideal solution is rare, but some solutions nearly behave as ideal solutions. So that solutions are example. So these solutions are behave as a ideal solutions. N-hexane and N-heptane, mixture of N-hexane and N-heptane. And the second one, bromoethane, mixture of bromoethane and chloroethane. And third one, mixture of benzene and toluene. Examples of ideal solutions. So the mixture of N-hexane and N-heptane, and the second one, the mixture of bromoethane, chloroethane, and the mixture of benzene and toluene. So these solutions are behave as a ideal solutions. Now let me take the plot. So for ideal solutions, the plot between the mole fraction and vapor pressure. On y-axis we are taken vapor pressure, on x-axis we are taken mole fraction. So at this place the mole fraction of A component is 0 and mole fraction of B component is 1, and at this place the mole fraction of component A is 1 and the mole fraction of component B is 0. And this is the line for component A. So here component A partial pressure is equal to component A pure vapor pressure into component A mole fraction. And this is the line for B component. Component B partial pressure is equal to component B pure vapor pressure into mole fraction of component B. And this is the total pressure. The total pressure P is equal to component A partial pressure plus component B partial pressure, and this is the component A pure vapor pressure and this is the component B pure vapor pressure. P naught B, and this one is the P naught A. And here this is the P naught A position and this is the P naught B position. So here we concluded that the component B is high volatile because the component B pure vapor pressure is more than the component A pure vapor pressure. So consequently the component B is the more volatile than the component A. So here PA is equal to P naught A into XA and PB is equal to P naught B into XB and P ideal is equal to PA plus PB. So these are for ideal solutions. For ideal solutions, PA is equal to P naught A into XA and PB is equal to P naught B into XB and P ideal is equal to PA plus PB. And next second one, non-ideal solutions. So the solutions which are not obey Raoult's law, entire range of concentration, are known as non-ideal solutions. The solutions which are obey the Raoult's law are called ideal solutions. The solutions which are not obey the Raoult's law are called non-ideal solutions. And these non-ideal solutions are further classified into two types on the basis of deviation from Raoult's law. Number 1, A, positive deviation. Positive deviation. And number 2, B, negative deviation. And the non-ideal solutions properties. The properties are, when the two components, I am taking two components, component A and component B. When these two components are mixed to form solution, the change in enthalpy will not be zero. So delta mix H will not be 0. But in ideal solutions, the delta mix H is equal to 0. But in non-ideal solutions, the delta mix H not equal to 0. And it may be negative. It may be negative. The delta mix H may be negative or heat released. Negative means heat released. Heat released means delta mix H is less than 0. Negative means delta mix H is less than 0, means heat released, or it may be positive. It may be positive, or heat absorbed. Heat absorbed means delta mix H is greater than 0. So here volume of solution not equal to sum of the volumes of the pure components. The volume of solution not equal to sum of the volumes of the pure components, means delta mix V not equal to 0. In ideal solutions, the delta mix V is equal to 0. but in these non-ideal solutions delta mix V not equal to 0. So there will be some expansion or compression in dissolution of liquids because components A B having different shapes, that A B having different shapes and size and character. But in ideal solutions, the A and B components having same size, same shape and same character. But in non-ideal solutions, that component A, component B having different shapes and different size and different characters. So here I consider that component A as a solvent and component B as a solute. So in pure component A, the intermolecular attractive interactions are A and A. In pure component A, the intermolecular attractive interactions are A and A, means the interactions between solvent and solvent. And in pure component B, pure component B, in pure component B, the intermolecular attractive interactions are B and B, means the attractive interactions between the solute and solute. If we mix both components to get the solution, so in that solution we have three types of interactions. We are getting the solution. If we mix both components, we are getting the solution. So in that solution we have three types of intermolecular attractive interactions. Three types. Those are AA means between the solvent and solvent, and BB means between the solute and solute, and AB means between solvent and solute. So if these three intermolecular attractive interactions are not same, it leads to formation of non-ideal solutions. Means in that non-ideal solutions, so these three intermolecular attractive interactions are not same, but in ideal solutions these three intermolecular attractive interactions are same between the solvent solvent and solute solute and solvent solute. So this is about liquid solutions. So in that liquid solutions, ideal solutions and non-ideal solutions. So this non-ideal solutions also classified into two types: positive deviation and negative deviation.